Environmental Systems and Societies for the IB Diploma program. Pearson book. Moving on to Chapter 6, Atmosphere and Climate Change. 6.1, Introduction to the Atmosphere. The guiding question: how do atmospheric systems contribute to the stability of life on Earth? And here we have a list of the key understandings. 6.1.1, the atmosphere. The Earth's atmosphere is the outer limit of the biosphere, and its composition and processes support life on Earth. That's related to Topic 2, Section 2.1.1. The atmosphere is a mixture of solids, liquids, and gases that are held to the Earth by gravitational force. We don't always often think about the atmosphere as having solids in it. We'll come back to that. These gases are redistributed around the world through physical processes, such as wind. The atmosphere extends upwards from the Earth up to a height of about 80 kilometers. The composition of the atmosphere is fairly constant, unchanging, with 78% nitrogen gas, 21% oxygen gas, 0.9% argon gas, and a variety of other trace gases such as water vapor, carbon dioxide, helium, and ozone. In addition, there are solids such as dust, ash, and soot. Air moves from areas of high pressure to areas of low pressure. This is known as the pressure gradient force. The strength of the wind varies with the differences in pressure. Where there is a large difference, for example, in a tropical cyclone or hurricane, wind speeds tend to be very high, often exceeding 119 kilometers per hour. There is no outer limit for the atmosphere, but most weather occurs in the lower 16 to 17 kilometers of the atmosphere in the layer known as the troposphere. In the troposphere, temperatures fall with height above the Earth's surface, on average 6.5 degrees Celsius per kilometer. Certain gases are concentrated at particular heights of the atmosphere. You can see here in figure 6.2. Ozone occurs mostly around 25 to 30 kilometers above the surface and is important for the filtering of harmful ultraviolet UV radiation. So here in figure 6.2, you see the vertical structure of the Earth's atmosphere. The exosphere, thermosphere, mesosphere, stratosphere, troposphere. 6.1.2, differential heating and the tricellular model. The Earth's energy is mostly derived from the sun. Incoming solar radiation is referred to as insolation. In some places, there may also be important local sources of energy, such as heat islands in urban areas and geothermal heat in tectonic regions, areas of the Earth that are close to tectonic plate boundaries, or where the plate is thin enough to allow geothermal heat to rise to the surface. The fundamental factor causing atmospheric circulation is the unequal heating with latitude. Between 38 degrees south and 38 degrees north, there is an excess of energy, whereas polewards, or closer to the poles, there is a deficit of energy. Energy is transferred from low latitudes to high latitudes, so closer to the equator, to the higher latitudes, further from the equators, closer to the poles. So from low latitude to high latitude to balance this unequal heating. Air moves in towards centers of low pressure, convergence, rises, and then spreads out when it reaches the tropopause, not the same as the troposphere. Go back to this. It's called divergence. When air converges at a high altitude, it sinks and forms high pressure at ground level. From there, it moves outwards, diverges, at ground level. And this you can see in 6.3, which is on the other page if you're following along in the book. I'll put it here. The global pattern of winds is thus determined by the location of pressure systems. However, there are also seasonal differences due to the position of the sun. At the equator, warm air rises, forming an area of low pressure. It then moves toward the north and south poles. In subtropical areas, which is 20 to 30 degrees north and south, high pressure areas are formed when the air sinks because it has become cold and dense. And here we have some key understandings. Geothermal heat is thermal energy in the Earth's crust. Remember, the Earth has a molten core, so inside the Earth things are very, very hot. Latitude is the position of a place on Earth relative to the equator, north or south. Some of this air moves from the subtropical areas back to the equator to replace the rising air. This convectional cell is known as the Hadley cell. At each pole, a second cell, known as the polar cell, has cold, dense air sinking, polar high pressure, and moving outwards to the mid-latitudes. Between each polar cell and Hadley cell is a third cell, known as the Ferrel cell, which is driven by the movements in the polar and Hadley cells. It's also related to topic 2 from section 2.4.5. The action of the three cells together forms a model of atmospheric circulation known as the tricellular model, figure 6.4. (6.1.3) The effect of greenhouse gases and aerosols. Greenhouse gases, GHGs, found in the atmosphere include water vapor, carbon dioxide, tropospheric ozone, methane, or methane, and nitrous oxide. Black carbon is also found in the atmosphere as an aerosol. Greenhouse gases permit incoming short-wave radiation from the sun to pass through, but can absorb long-wave radiation since incoming solar radiation and outgoing long-wave radiation operate at different wavelengths. You can see figure 6.5, incoming solar radiation and outgoing long-wave radiation, a comparison of wavelengths. Most greenhouse gases lead to a warming effect, but there can also be a cooling effect. We'll look at figures 6.7 and figure 6.8. We'll come to those. This can occur due to the amount of aerosols in the atmosphere. Many of these aerosols, such as sulfur emissions, are produced by humans. The aerosols can have a direct effect on the proportion of solar radiation reaching the Earth's surface. Aerosols can have a local or regional effect on temperature. For example, many industrial areas have not warmed as much as expected with an increase in greenhouse gases. This global dimming, or regional dimming, can be caused by the increase in cloud cover caused in part by aerosol loading and in part by increased water vapor, which may reflect large quantities of solar radiation away from the Earth's surface. Black carbon, an aerosol. Black carbon, see figure 6.6, is formed from the incomplete combustion, means burning, of fossil fuels, biofuels, and biomass. Approximately 20% of black carbon is emitted from burning biofuels, 40% from fossil fuels, and 40% from open biomass such as savanna and rainforest. Black carbon is very fine particulate matter of diameter less than 2.5 microns. However, black carbon only stays in the atmosphere for days or weeks before being removed by rain or snow. The impacts of black carbon on the climate include direct effects. When suspended in the atmosphere, black carbon absorbs sunlight and reduces albedo. Semi-direct effects. Black carbon absorbs insolation and affects cloud cover. Snow and ice albedo effects. When deposited on snow or ice, black carbon reduces the albedo. This can lead to a positive feedback effect where the decreased albedo leads to increased surface temperatures, which in turn decreases ice cover and reduces the surface albedo. Indirect effects. Black carbon can cause indirect changes in absorption or reflection of solar radiation through changes in cloud cover. According to the Intergovernmental Panel on Climate Change, the IPCC, the combined direct and indirect snow albedo effects make black carbon the third largest contributor to radiative forcing, which we're gonna get to. Since pre-industrial times, black carbon is also a significant contributor to Arctic ice melt. The IPCC estimates that the soot on snow change in albedo could be responsible for up to 25% of global warming. Radiative forcing. Radiative forcing is a measure of the balance between incoming solar radiation and outgoing long-wave radiation. A positive radiative forcing means that the Earth is receiving more incoming energy than it is radiating back out to space. Radiative forcing varies with insolation, albedo, and the concentration of greenhouse gases. Hydrochlorofluorocarbons, HFCs, are compounds, chemicals, that contain only carbon, hydrogen, chlorine, and fluorine. These are temporary alternatives to chlorofluorocarbons, CFCs, have shorter atmospheric lifetime, and release less reactive chlorine to the stratosphere. Hydrofluorocarbons, HFCs, are synthetic gases mainly used for cooling and refrigeration. They are powerful and short-lived, but do not contain chlorine, so do not destroy stratospheric ozone. 6.1.4 The Greenhouse Effect. The greenhouse effect is the natural process by which greenhouse gases and aerosols in the atmosphere absorb and re-emit long-wave infrared IR radiation that has been reflected from the Earth's surface back to Earth, thereby warming the atmosphere. The greenhouse effect is the natural process in which greenhouse gases and aerosols trap a proportion of outgoing long-wave radiation, which keeps the Earth warm enough to support life. The enhanced greenhouse effect is the increase in greenhouse gases in the atmosphere, largely due to human activities, which trap increasing amounts of outgoing long-wave radiation, thereby leading to global warming. The greenhouse effect makes the Earth warmer than it otherwise would be and makes life possible. Without the greenhouse effect, the Earth would be too cold for most life forms to survive. Although the gases, oxygen and nitrogen, make up the bulk of the atmosphere, they do not absorb or emit long-wave radiation. In contrast, water vapor and some other minor gases absorb some of the long-wave radiation emitted by the Earth's surface and act as a type of blanket. These are the greenhouse gases, without which the average temperature on Earth would be about minus 18 degrees Celsius rather than 15 degrees Celsius. Okay, so the average temperature on Earth is 15 degrees Celsius, and this is because we have greenhouse gases. This blanketing effect is known as the natural greenhouse effect, which is a normal part of the Earth's climate and has existed for nearly the whole of the atmosphere's history. The enhanced greenhouse effect refers to the increase in greenhouse gases such as carbon dioxide and methane due to human activity. This leads to temperatures on Earth being greater than they should be, causing the effects known as global warming, climate change, climate crisis, global heating. Choose your expression. You can see this in figure 6.9. The natural and enhanced greenhouse effects. Carbon dioxide and methane and water vapor in the atmosphere limit the amount of heat escaping from Earth's surface. Although carbon dioxide is the most important greenhouse gas, other gases such as methane and nitrous oxide and tropospheric ozone also contribute to the enhanced greenhouse effect in global warming. The combined impact of these minor greenhouse gases adds a warming equivalent of about 60% of carbon dioxide. Nitrous oxide is a direct greenhouse gas. There are other oxides of nitrogen as well, and the role of these pollutant gases in the greenhouse effect is complex, and they are described as indirect greenhouse gases. 6.1.5. The atmosphere is a dynamic system. The atmosphere is a dynamic system, and the components and layers are the result of continuous physical and chemical processes, including global warming and the production of ozone from oxygen gas. The atmosphere is a complex, open system with inputs of solar radiation, water, aerosols such as dust and salt, and over geological time, comets and meteors. Even if we consider the Earth as a closed system, the atmosphere is influenced by many factors, including Milankovitch cycles, latitude, altitude, proximity to the sea, winds and pressure, ocean currents, ice sheets and glaciers, aspect, tectonics, geothermal energy, natural hazards, vegetation changes, and human impacts. The stratosphere is a layer of the atmosphere that extends from the troposphere, the lowest layer, to about 50 kilometers above the Earth's surface. The stratosphere is very dry and lacks clouds. The stratosphere contains the ozone layer, which absorbs some of the high-energy UV radiation emitted by the sun. Physical processes include air movements and the greenhouse effect. Pressure differentials are the basic cause of air motion. In addition to the pressure gradient force, winds and ocean currents are affected by the Coriolis force, which is a deflecting force caused by the Earth's rotation. The strength of the force increases with distance from the equator. It causes winds to be diverted to the right of their path in the northern hemisphere and to the left of their path in the southern hemisphere. Chemical processes. In the stratosphere, high-energy UV radiation strikes oxygen molecules and splits them into two single oxygen atoms. One of these freed oxygen atoms can then combine with an oxygen molecule to form a molecule of ozone. You can see this in figure 6.10. This is also known as the ozone-oxygen cycle. Stratospheric ozone absorbs some of the high-energy UV radiation emitted by the sun. 6.1.6. Atmosphere and altitude. Molecules in the atmosphere are pulled towards the Earth's surface by gravity. Because gravitational force is inversely proportional to distance, i.e., as distance increases, gravitational force decreases, the atmosphere becomes thinner with distance from the Earth's surface. Air motion is dependent on pressure systems. In areas of high pressure, air is generally descending, whereas in low pressure systems, rising air cools as it expands and increases the vertical temperature gradient. The overall vertical change in temperature over time is known as the lapse rate. The average lapse rate for the Earth is 6.5 degrees per kilometer, slightly less than 1 degree Celsius for about every 100 meters. However, lapse rates vary with the level of moisture present in the air. The temperature of dry air may decrease at a rate of 10 degrees Celsius per kilometer, whereas saturated air may decrease more slowly at rates of between 4 degrees and 9 degrees Celsius per kilometer. Winter rates are generally lower, and in continental areas may even be negative, caused by excessive cooling over snow surfaces. So mountain climbers require oxygen tanks at high altitude due to the thinning of the atmosphere. 6.1.7 Milankovitch cycles. There are 3 types of Milankovitch cycles relating to the shape of Earth's orbit, angle of tilt, and axis of rotation. Milankovitch cycles affect how much solar radiation reaches the Earth and lead to cycles in the Earth's climate that last between tens and hundreds of thousands of years. Milankovitch cycles are very long cycles in the Earth's orbit around the Sun, the tilt of its axis, and the wobble of the Earth in space. They do not account for the more recent changes associated for global warming. Milankovitch cycles can lead to positive feedback changes, such as decreasing concentrations of atmospheric carbon dioxide with cooling and glaciations, or increasing concentrations of atmospheric carbon dioxide with warming and interglacial conditions. Okay. Link that to 1.2 systems, chapter 1.2. The 96,000 year stretch. It's figure 6.12a. The Earth's orbit around the Sun varies from being more circular to more elliptical over a cycle of about 96,000 years. Glacials are phases in the Earth's climate when glaciers and ice caps increase in extent. During the last glacial phase, glaciers and ice caps covered 30% of the Earth's surface. Now they cover about 10%. Interglacials are warm phases during an ice age when ice covers less of the Earth's surface. As ice currently covers only about 10% of the Earth's surface, we are in an interglacial phase. The 42,000 year tilt. The Earth's axis is currently tilted at 23.5 degrees, so the tropics of Cancer and Capricorn are found at 23.5 degrees north and south, respectively. However, the tilt can vary between 21.5 degrees and 24.5 degrees. You can see this in this figure. When the tilt increases, summers become hotter and winters are colder, favoring interglacials, the warm phase. Okay. So lines of latitude are parallel lines indicating how far north or south of the equator a place is. The Tropic of Cancer is a line of latitude located at 23.5 degrees north of the equator. The Tropic of Capricorn is a line of latitude located at 23.5 degrees south of the equator. The 21,000 year wobble. As the Earth slowly wobbles in space, its axis moves in the shape of a circle every 21,000 years. At present, the orbit makes the Earth closest to the Sun in the northern hemisphere's winter and furthest away in summer. These conditions favor the growth of glaciers. In contrast, when the Earth is closest to the Sun during the northern hemisphere summer and furthest away during the winter, conditions are warmer. This helps explain in part the present warm interglacial that the Earth is experiencing. The greenhouse effect is misunderstood by many people. It is a natural process which is vital for life on Earth. In contrast, the enhanced greenhouse effect has a negative impact and can lead to global warming. I'm not sure why that box was placed right there in the text, but there it is. Nice reminder. 6.1.8 Hothouse Earth. And this is kind of links to biodiversity and evolution in chapter 3. Albedo refers to the reflectivity of a surface. Light-colored materials such as snow and ice are highly reflective and have a high albedo, sometimes 75 to 90%. Dark, wet soil has an albedo of 5 to 15%, and so may absorb much of the incoming solar radiation. The ice albedo feedback is a positive feedback mechanism whereby a decrease in temperature may lead to an increase in the area covered by light-colored materials and so increase the albedo. This means it reflects more of the incoming solar radiation, and so the area gets cooler. This can be very important for regional and global climate change. On the other hand, if warming occurs, snow and ice cover could be reduced, meaning light-colored surfaces would be replaced with the darker surfaces of bare ground and soil. The albedo would decrease and more solar energy would be absorbed, leading to further increases in warming. The Quaternary period is the geological era that started about 2.58 million years ago. Climate change has occurred naturally during the Quaternary, but the recent anthropogenic, human-induced changes have occurred more rapidly than any natural changes have ever happened. In a report titled Trajectories of the Earth System in the Anthropocene, Stefan et al., 2018, they argue that the term global heating should be used instead of global warming. The report states that there is a risk that the Earth is entering a new climate phase called hothouse Earth, in which the climate will stabilize at a much higher temperature than desired by scientists. It suggests, as does the UK Met Office, that temperatures could be as much as 4 to 5 degrees Celsius higher than pre-industrial levels since around 1800, and warns that sea levels could be up to 1 meter higher than today. This would be much greater than anything over the last 1.2 million years. Such a change may be considered part of the new geological era known as the Anthropocene, in which human activities play a major part in physical processes on Earth. This connects back to topic 3. The Earth's climate may change so much that it will be taken out of the glacial-interglacial cycles that have characterized the Holocene. In the words of the report, the Earth system has likely departed from the glacial-interglacial cycle of the late Quaternary, and it would take in the order of 100,000 years for conditions to return to their pre-perturbation levels. The Anthropocene is the period of time during which human activities have impacted the natural environment to such an extent as to form a new geological era. Tipping points. The Hothouse Earth report suggests that even an increase of just 2 degrees Celsius could be enough to trigger a series of positive feedback mechanisms called tipping points. Go back to topic 1 and topic 2. In places such as the Arctic and around Antarctica, which could throw the Earth out of stability. However, there are uncertainties about these suggestions. For example, increased atmospheric carbon dioxide has led to increased plant growth, and therefore a greater carbon sink. On the other hand, rising temperatures make the plant's leaves hotter, which makes enzymes lose their quality. They are denatured, reducing photosynthesis. Furthermore, atmospheric warming raises soil temperatures, increasing microbial respiration, and thereby releasing carbon dioxide back into the atmosphere. Increased temperatures will cause permafrost melting and the release of some methane frozen within peat. However, the scientists do not agree on how much carbon dioxide and methane will be released, as this will depend partly on the size of the temperature increase. The Earth has entered very uncertain times. In wetlands, soil minerals are forced to metabolize under anaerobic conditions. This leads to methane production. Warming causes wetland soils to warm and/or flood, releasing methane into the atmosphere. Flooding in rice fields cuts off the oxygen supply from the atmosphere to the soil, resulting in anaerobic fermentation of soil organic matter. Methane is the end product of anaerobic fermentation. 6.1.9 Evolution of Life and the Development of the Atmosphere. The evolution of life has changed the Earth's atmosphere. The Earth's first atmosphere was formed by emissions of gases trapped in the Earth's interior. This still occurs today in volcanic eruptions, but on a much smaller scale. The earliest atmosphere developed about 3.5 to 4 billion years ago. It was almost certainly developed as the Earth's interior melted to form a core, mantle, and crust. This early atmosphere probably had large amounts of nitrogen, carbon dioxide, methane, and ammonia, but virtually no oxygen. The earliest oxygen was released by geological and biological processes. For example, prokaryotic organisms produced oxygen as a byproduct of photosynthesis. Iron ore formation began about 1.8 million years ago when iron was dissolved in seawater. Photosynthetic organisms take in carbon dioxide and produce oxygen. However, initially this oxygen did not build up in the atmosphere, but instead was taken up in rocks as a result of chemical reactions. As these organisms evolved, the carbon dioxide content of the atmosphere reduced and increasing amounts of oxygen were released into seawater, where combined with dissolved iron to form iron oxides such as hematite and magnetite in banded iron formations and continental red beds. Indeed, most of the oxygen produced over geological time is trapped inside rocks. When the mineral olivine comes in contact with water, it starts chemical reactions that can use and lock up oxygen. However, as the Earth's continental crust evolved into one similar to that of today, olivine virtually disappeared. Without olivine to react with water, oxygen was allowed to accumulate, first in the oceans and then in the atmosphere. Although you need to know how the evolution of life changed the atmosphere, you do not need to remember the timings of oxygenation. The composition of the present atmosphere needed the formation of oxygen. The atmosphere was marked by a decrease in atmospheric carbon dioxide and an increase in oxygen due to life processes. There are two basic processes that produce oxygen gas in abundance. 1. The breakdown of water into hydrogen gas and oxygen in the presence of UV radiation. 2. Plant photosynthesis uses solar energy, carbon dioxide, and water to produce carbohydrates and oxygen as a byproduct. Photosynthesis led to high oxygen levels in the current atmosphere. As levels of oxygen increased in the atmosphere, organisms evolved to use oxygen in aerobic respiration. This change allowed the evolution of very complex multicellular life forms. For example, once oxygen built up to 1 to 2% of its present levels, photosynthetic prokaryotes, single-celled organisms without a nucleus, were replaced by more efficient eukaryotes, organisms whose cells had a nucleus. Once efficient photosynthetic organisms evolved, they had a major impact on the atmosphere, reducing carbon dioxide levels and further increasing the amount of oxygen available. The release of oxygen by cyanobacteria was responsible for changes in the Earth's atmosphere and for evolution. Cells that could access oxygen had a notable metabolic benefit. Most life on Earth needs oxygen to produce usable chemical energy in the cell, necessary for growth and reproduction. As oxygen levels increased, the evolution of life progressed.